Yes, he's just going to grab some.
If you want these two, I'll move over and see.
Good evening, everyone.
Good evening.
Everyone say hi, Amanda. Hi. Awesome. Thank you for that. My name is Amanda Thomas. I am the events manager at OMSI, and I would love to welcome you to a very special science pub. Yay! As you probably know, we are here with a guest from out of town, from Illinois. Theodore Gray is here to talk about mad science. Theodore Gray presents daredevil science you can do at home, but probably shouldn't. And I mentioned earlier that we have some of his books available. I don't know if any of you have seen this book. It's pretty cool. There's all sorts of, really cool demonstrations, a couple of which he's going to be doing here this evening. There's chapters that are called like Raw Power and Playing with Fire. So heartily endorsed by by all of us science geeks. He also has a really beautiful book called The Elements here. Yay! Both of these are available at the table in the back. The Elements goes through all of the elements in the periodic table and shows pictures of things that are made out of them. You'll be seeing a lot of those images this evening, and heartily recommended for both of these books. And so Theodore Gray is a element collector. He took most of the photos in the book. We at OMSI have a periodic coffee table. Yeah, it's the periodic table on a coffee table. It's cut out to be like that, using the images from his book. It's really fantastic. So we're very excited to have him here this evening. Okay, so without any further ado, I'm going to invite our speaker for this evening, Theodore Gray. He's a fantastic person. I'm really excited to have him up on stage. Take it away, Theodore.
Hello. Do I have my microphone on? Great. Can you all hear me?
Yes.
Great. So I give a lot of talks, like to all kinds of different groups all over the world. Usually, like a little bit more dignified or something. By which I mean not as much drinking. So about a week ago, somebody sent me an email asking if they could bring their 6-year-old to this event, and I said, sure. You know, I'm not like. I don't know, that'd be fine, and they probably would enjoy it. And my publicist said, oh, no, you can't do that because this is a 21 and only event and there's no kids allowed. And my immediate thought was, wow, that like opens up all kinds of possibilities that I can't normally get away with in a talk. And then I arrived here and there's like kids everywhere. So I'm thinking, well, now what do I do? Sorry.
Talking falsetto.
Hello. Is that good? What? Is this good? Can people understand me? Okay. Anyway. Yeah. So like this is my entire talk is now sort of a question. But I think we can make it work. So we're gonna restrict ourselves to one reference to illegal drugs, but it will be very clinical and scientific, and one slightly off-color double entendre, which will just go right over their heads. But before I get to the actual main content of the talk, I want to give you a little bit of background, like how did I end up here? Because I'm actually in the software business, and I don't really do this for a living, but how did we get here? How did I get here? This started with a wonderful book, Uncle Tungsten by Oliver Sacks. Highly recommend it. If you haven't read it, you should all go out and buy it. It's a great book. As well as all his other books, but this one in particular. And in this book, he describes a periodic table that he used to go visit in the Kensington Science Museum when he was a kid. And I'm not the only one who read this passage. It's like a little paragraph that talks about this periodic table and it had elements on it. And I thought, oh wow, it's a table and there's like samples of the elements on this table. And isn't that a fantastic idea to have a periodic table that's a table? And then like you read the next paragraph and you realize, no, it was just confusing the way he wrote it. It's actually on the wall and the samples are behind glass just like everybody else's periodic table display. This was just really disappointing because I had this vision of a periodic table with samples on it. So I thought I need to fix this because as far as I could tell, it didn't exist anywhere. Nobody had ever built, that I could tell, and the internet knows, a periodic table table. So I built one for my office. It took a while, but we got it done. It's got little engraved letters everywhere. By the way, this sounds really funny to me. Are you guys understanding me?
Yep.
Does it sound okay? It sounds like it's echoing or something.
It does, but we can understand you.
It sounds like you suck some helium, but...
Yeah, that's what it sounds like to me too.
Yep.
But I don't actually sound like that, I don't think. At least not. Anyway, so this is what I ended up with. About a year later, it looked like this because of the fact that I also discovered eBay around. And eBay is just mind-blowing if you're an element collector. I thought it would take me 30 years to get them together, and just eBay. So I could, but then I'd have to hold it.
Well, yes.
All right. Okay. Well.
That's better. Yeah, but
Okay.
you
Is
sound
this
better.
better?
Yeah.
Okay. Well, gosh, I've never in my life actually used a handheld microphone for a talk. We'll see how this goes. Okay. So another, a couple years afterwards, it had overflowed the table, and now I have these display cases. We're now up to 3 actually in my office of these display cases. This picture is slightly out of date. This was Oliver Sacks who came to visit my periodic table, and who every year or two asks me, is it really my fault that you got into this? And I say, yes, if you'd written that passage more clearly, I wouldn't be here. So this is the 2002 Ig Nobel Prize in Chemistry. The award ceremony
Prize this year is awarded to Theodore of Wolfram Research in Champaign, Illinois, for gathering many elements of the periodic table and assembling them into the form of a 4-legged periodic
That guy up there on the right is
table.
the actual Nobel Prize winner. They get to hand out the Ig Nobel Prizes. We won't watch the whole thing. They have a great system though. When you do the acceptance speech at the Ig Nobel Prize, there's this little girl, she's about this high, and she's called Miss Sweetie Poo. And if you go over 2 minutes, she comes over on the stage and starts saying, "I'm bored, please stop." And she doesn't stop until you do. It's really, really effective. Anyway, so this was like the early 2000s. And I had an unusual collecting hobby, so there was the law that requires me to have a website in which I showcase my peculiar collecting hobby. Periodictable.com wasn't available, so I got periodictable.com and made a cheesy late 90s style website. And shortly thereafter, I got this call from the editor-in-chief of Popular Science magazine asking if I would like to write a column. And I said, why are you calling me? But I guess they liked my website or something. So I started writing this column, which I've been doing ever since. It kind of is one of the things that you stumble into and then it's hard to stop. And we're going to get to that in a minute because that's the origin of my book. Anyway, so then, after a while, it became clear, I had like more pictures of elements than anybody else on the planet, not to mention more elements, and I had a periodic table. I felt that I needed to have periodictable.com. It just wasn't right. And it took about a year, because once somebody has a domain that's that good, it's really hard to wrestle it out of their hands, even if they aren't, making, a lot of money off of it. So it took a year, a lot of, moral suasion and a little suitcase of cash and dedication, and I finally got periodictable.com and put up, I think, a much nicer looking website. And then I thought, I have a lot of pictures, I should make a poster. But that was kind of a scary proposition because I'd never been a publisher before. And it was like $15,000 to do a print run of posters, which seemed like a really foolish thing to do with that much money. But, you know, what the hell. So I did it anyway. And made that back in 2 weeks because of one post on Slashdot, which is like, wow. The internet actually works. You know, you read all these stories about people can make money on the internet, and wow, I was surprised. So let's see. Oh, that went. What were we looking at? I was one slide behind. This is the poster. They made a poster. Kept taking pictures. I actually hired a guy to take pictures for me because I was too busy for my hobby. So my hobby acquired an employee. So the next step was a book, The Elements. I think she held up a copy of it. It's really nice. It's basically the poster, only instead of one picture, every element gets a whole 2-page spread, and you should really have a copy because it's really nice. Each element gets, you know, one big picture and then some smaller pictures with explanations about them. Some of the kind of more popular elements get 2 entire pages, 2 full 2-page spreads. But the thing that people who are reading the print book may not realize is that every one of the photographs in that book, every single one of them, with 2 or 3 exceptions, is a single frame out of a complete 360-degree rotation of that element. 720 frames taken all the way around a complete circle on an extremely elaborate turntable, which I built for no discernible reason. Other than it seemed like, I don't know, Apple had come out with QuickTime VR a while ago, and I kind of thought, I should do something with that. So, this is what the elements actually look like. This is what I have as raw material. In order to produce a print book, we had to just really strip it down. But imagine if you had a book like this, except it actually made use of all of those 360-degree rotations. Imagine if this was, you know, rotating, or better yet, if you could take your finger and turn them under your own control. It might look something like this. The problem is that there was no deployment platform on which to do that. You can't really put it on the web because nobody will pay you for it. It's too much work to do for free. You can't sell ebooks on, you know, desktop computers because nobody wants them, nobody will pay for them, and there's no distribution mechanism. So there just wasn't any way to do this really. And I thought about it, and I thought, I wish somebody would come out with a ebook reader that was not a Kindle, that would have like a real screen that you could actually do interactive, you know, images on. And then, as is often the case when the world is waiting for something, Steve Jobs, he kind of comes from this higher realm and he descends and he gives the world a product that it didn't know it wanted, but that is somehow impossible to live without. This, of course, is the iPad. And this is a simulation of an iPad version of the Elements book, which I think we're going to skip the actual demo just in the interest of time. Maybe if we have a little time later, I'll do it. In the real thing, all of these are actually under your control. You know, you take your finger and you kind of spin them. And it's, you know, basically it's Harry Potter's version of the book. That was kind of what I was thinking is, you know, if Harry Potter got my Elements book out of the Hogwarts library, what would it do? And the answer is, these are objects. You want to be able to pick them up and look at them. And that's what his book will do. So that's what the iPad version does. That's the closest thing we've got to magic right now. It also does it in stereo 3D. So you can actually, if you have little glasses, you can see them popping off the screen in 3D. The other thing that we can do in an electronic version of this book that was not possible in print is to have a theme song. And here it is. 1959, Tom Lehrer recorded the song
There's
for
alloy,
us.
arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium.
I always kind of wondered if he actually got them all, or if he missed one.
Titanium, and indium, and gallium, and iodine, and
I
thorium.
started making this video and I realized if he did miss one, the video is screwed, because if he's building the periodic table and if he forgot an element in his song in 1959, my video would not finish. But
there's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, kryptonium, and radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium.
by the way, when they played this,
These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Yes, so he got them all. And I should mention, when they played this song at the Ig Nobel Award ceremony in Harvard, you could hear the audience singing along, which gives you an idea of just how monumentally nerdy the Harvard student body is. So believe it or not, he is actually not dead yet. He's 82 now, and I made a deal with him. I traded him an iPad for the rights to that song to put in my app. This is I guess it's still not. So this is a shot from one of the Apple commercials. Apple really likes this thing because it's a good example of why you should not buy a Kindle if you want to like see what the future of ebooks is like. It doesn't work on Kindles. Anyway, so that's kind of the elements track of things. The other thing that I was doing that whole time was writing this popular science column, which it's one page. It's very glossy. It's very highly produced. It started out with, they gave me about 500 words, but then they got a new graphic designer, and I'm down to like 350 because that was too much depth, I guess. It's a column typically about chemistry. It's not necessarily limited to chemistry, but mostly it's about chemistry because that's the only thing I actually know anything about. And one of the things that it really tries to do is to relate interesting scientific principles to something that is actually that the common person can identify with. So a good example of that is hydrogen soap bubbles. So if you've ever seen been in a chemistry class with a halfway decent chemistry teacher, at some point during the year, they will have filled up soap bubbles with hydrogen gas and lit them in the classroom. And if they were like one notch better, they would have then started mixing in oxygen with the hydrogen. And we'll see a little demonstration of it here. So this is pure hydrogen. And you can't really appreciate the sheer beauty of these. They're like jellyfish made out of fire, and they're just beautiful. The next thing you do is you start mixing in oxygen. I need a better slow motion camera, but they're expensive. So hopefully soon we're going to get a mixture of oxygen and hydrogen. And when you pre-mix these two things, they react a lot faster. I believe the next one, yeah, here we go. This one scared me because I had to, like, it wasn't detaching, it was getting bigger and bigger and bigger. And I finally took a stick. And that ricocheted off the countryside. And you have to understand, I live in Illinois, where it's completely flat. So this sound was somehow loud enough to bounce off of nothing. But anyway, it is a spectacularly powerful explosion when you have, half a cubic foot or so of mixed hydrogen and oxygen. But that was not a good enough reason for me to be able to write about that in my column, because my editor said, well, that's great, but what does this have to do with the daily life of anybody who mixes hydrogen and oxygen? And it took me, in that case, about a year to figure out how I should be allowed to write about it. And the answer is, it's an explanation for why, in the Midwest in particular, every once in a while somebody comes back from vacation to find that their house has been completely demolished and the roof is in the basement and the walls are out in the fields. The house is always surrounded by fields. Nobody's ever hurt. And the reason is that in the rural areas in the Midwest, houses are heated with propane. There's no natural gas, and unlike on the East Coast, they don't use heating oil, they use propane. Propane is heavier than air and highly viscous. If there's a gas leak, it will accumulate in the basement and slowly build up until it reaches a pilot light of something, at which point it will detonate. It doesn't happen when anybody's home because they add a really incredibly smelly compound to it. So you notice it long before the gas reaches any sort of explosive concentration. Every once in a while, yes, people are killed, but it's very rare. Almost always it happens in unoccupied houses. And so this answers the question, why is it the same gas that burns gently and slowly in your furnace or stove explodes violently under other circumstances? The answer is, it's when it's pre-mixed with air before it's ignited, then it explodes. If it's burning as it mixes, then it produces a gentle flame. And that's easily demonstrated in an entertaining way using the hydrogen bubbles. Other people are less concerned with there needing to be a reason to do this. So I'm going to show you next a video from Japan where I was on one of those shows last year. Turn the sound up a little. That's apparently what I sound like in Japanese. This is a different demonstration which I was going to do here, but it's really hard to see, so I thought it's actually better for you to see the video. I'll overdub the Japanese. So this is saying this is a genuine silver spoon that I've just given him. He's testing that. Now he's explaining it's an indium tin bismuth alloy, which melts at about 150 Fahrenheit or so. So it melts in hot water. And contains no mercury or anything like that. It's non-toxic. This is like a battle to see who's the greatest mad scientist.
じゃあ、三浦春馬君、宮根君お願いします。
これは魔法の泡なんだけど、試してもらえるかな。まず手を水で濡らして。
じゃあ、宮根君お願いします。
そしたら両手で泡をすくってみてごらん。
宮根君どんな感じでしょうか。普通の泡です。青な赤。
I'm saying like what are you afraid of? It's just so bubbly.
手を水で濡らしてから泡をすくってくれるかな。
じゃあ、宮根君お願いします。
What they don't know is that they switch the bubbles around on camera.
さっきはちょっと火力が弱かったみたいだから、今度は少しパワーを送ってみようかな。
絶対来んじゃん。
白い実験を見せるから10人ほど協力してもらえないかな。
By the way, that guy, his name is Denjiro. He's like the Bill Nye of Japan, I think. He's like a science performer. So now they got all these
左手を
kind of freaky Japanese people together.
順番に青をちゃんと手を伸ばしていって青をもらってからも腕は曲げないで。では皆さん泡同士がくっつくようにもっと
What's in there is actually a mixture. Turns out pure hydrogen burns too fast. So it's a mixture of hydrogen and butane.
腕を伸ばして
Tuned so that it burns at a good rate.
もうちょっと泡を足しましょう。そのくらいかな。皆さん手だけは離さないようにしてください。では行きますよ。火パワーを送ります。
That's like the Dick Clark of Japan. His name is Masai Sakai. He's apparently very famous.
次の三浦君の後、今回の案には燃えやすい水素を混ぜ
So
て
again, they snuck in a different batch of bubbles which had an oxygen-hydrogen mixture just for the last guy. Only in Japan, I think, could you get away with the fact that none of those people actually knew what was going to happen.
今日は知らない人から泡をもらってはいけないという
Anyway,
こと
moving
で
on. Oh darn, I should have put a slide in here to, this is my first adults only experiment. So this is, we're explaining ethanol, like how to make alcohol with a still. And I forgot to put in the beautiful picture that we got, the still picture we got from this. Turn the sound up.
You want to put it out?
No, get more shots. All right, now we'll put it out. Yeah, because the whole thing is completely fake. It was meant to be. I forgot, unfortunately, to put in the beautiful picture we had of this glass model of a still, but the boiling glass was actually just a flint glass flask that was not going to stand up to the heat at all. Actually, you know, this would be a good time now to have the demonstration, I think.
Fire.
Because so what we're going to do now is show you a related issue. The problem was that was not heat-resistant glass. And it didn't need to be because I knew we were going to get a shot. And I probably should have said put it out like 2 seconds earlier and we wouldn't have lost the whole apparatus. But it's fine because we got the shot. What we should have been using is Pyrex. Because Pyrex is resistant to heat, right? Pyrex is borosilicate glass. Which has a very low coefficient of thermal expansion and therefore doesn't crack when you expose it to temperature changes. Did you spot the factual inaccuracy? It's not Pyrex that's heat resistant, it's borosilicate glass. But Pyrex is so completely synonymous with borosilicate that, you know, it's just, if you say Pyrex, you assume heat resistant. And it turns out this used to be true, or at least used to almost always be true. But the Pyrex brand was recently sold several years ago to another company. And when you buy Pyrex measuring cups, like this, I just bought these yesterday at Walmart, Pyrex brand, right? This is not borosilicate. This is actually heat-tempered soda lime glass. And, you know, I find that fact absolutely shocking. I mean, Pyrex, you know, Pyrex is borosilicate. The company, if you look at their website, World Kitchens, they claim that Pyrex, since its inception in the 1950s, has not always been borosilicate. That some of it has always been heat tempered. And, you know, I don't have a piece of every single piece of Pyrex brand that's ever been made for the past 60 years. So it's possible that there has been some Pyrex that was heat tempered in the past. And they also make the claim that heat tempered glass is actually stronger than borosilicate, which is true, because the tempering introduces an internal stress in the glass that makes it very hard to break mechanically, and it increases its heat resistance somewhat. But I can tell you for an absolute fact that Pyrex measuring cups didn't used to be heat tempered soda lime. They used to be borosilicate. And the reason I can tell you that is because of a conversation I had with a person who I like to refer to as my underworld contact. She goes by the name Cody, which is not her real name. And for some reason, I actually can't remember now exactly why, I was discussing this question with her. And she said, oh yeah, we know that. We had to stop using that for cooking crack because they started splitting it after a while, at some point in the mid-2000s. All over the underworld, crack cocaine could no longer be made in kitchen-grade Pyrex measuring cups. And the reason is because there's a step in the synthesis. You put a little bit of baking soda solution, you put the powder cocaine in there, and you heat it up to boiling, like in a sort of double boiler thing, and you watch. I haven't actually done this myself. And you watch it, and apparently at some point it kind of turns oily, and it coalesces into the little rots that become crack. And at that point, you have to stop the reaction right away, which you do by dropping ice cubes in. So you subject it to a thermal shock from boiling to freezing instantly. And that will, not every time, but eventually cause them to fail. So they now have to steal beakers from labs instead of going to Walmart. And this is another example. I tried to get my editor to let me write about this scandalous fact that Pyrex wasn't borosilicate anymore for years, literally for years. And they said, oh, we don't do consumer protection articles. But when I told them about the crack, that was like, this is way more interesting. So we're now going to demonstrate what happens when you expose this stuff to excessive heat stress. Like I say, boiling to freezing will eventually crack it, but not reliably. If you want to do a photo shoot, this was actually in last month's Popular Science, or maybe the month before. You can see the picture that we got doing this. If you want it to happen reliably, you have to kind of increase the temperature stress somewhat. So we're going to use a blowtorch. Instead of ice water, we just use an eyedropper. Let's see, I have a minion, right?
Yes.
Excellent. But we're going to have to switch to this microphone because I can't hold this. No, we don't need the table. We're going to do it right here. Oh, but wait a minute. No, we need the protective gear.
Oh, I love that.
Okay, everyone, this is Elizabeth Dannon, lead chemistry educator at the at OMSI. She's got her purple vest on to prove it. So,
Hey, by the way,
and the chicken foot.
This coat is completely unnecessary, but they got it for me, and it's so cool. This is necessary because there will be glass flying. And this is necessary because I don't know what happens to the handle each time is a little different.
Oh, you're covering your mic. Oh, yeah. Yeah, pull it onto the here.
All the glass will hit me.
Okay, so I'm going to light this, or heat this. There's a non-zero but low probability of its cracking while I'm heating it. It's never actually happened yet, but I feel like it could. And once it's hot enough, I'm going to hand this to you. You're going to hand me the eyedropper. Anybody who is not confident in the fact that I don't think the glass is going to go that far should probably close their eyes or something.
It's like Science Gallagher.
I've never had it go more than a few feet.
They were the canary in the coal mine. They were like the first to notice. So
I hate this. I hate stuff that just might go any moment. I don't like to pop balloons either.
obviously you don't.
Okay, let's go for it.
That's not Pyrex.
Okay, so experiment. There's two things you learn from this experiment. One is that would not happen with Pyrex, sorry, borosilicate. The other thing is their quality control sucks because this is supposed to be highly stressed, heat-tempered glass, kind of like tempered glass windshields and glass. And when that stuff shatters, what is supposed to happen is that the whole thing crazes into a million little pieces. And about, in my experience, 4 out of 5 of these measuring cups, you'll actually end up all the way down to the tip of the handle, which is why I wear the glove, will shatter into a million little pieces. It'll just craze everywhere. You know, one out of 5 or 6 or so does this, which means it was not even tempered. You know, it's just glass.
Take it back and demand a refund.
So, yeah. Right, you can tell from the fact that it didn't craze that there was no good temper on it. It's really, I don't know, it's kind of sad.
We should have a run on Walmart returns.
The Pyrex brand for consumer use is no longer owned by Dow Corning. Okay. How are we doing for time, by the way? What time is it actually? Yeah, right. It's hot. That's why we have the wet canvas here to try to keep from burning the place down. Okay, so let me show you the next experiment that we're not going to do here. Where do we start here?
It's hooked up to a cylinder of oxygen gas.
Yeah, so this is what's referred to as a bacon lamp.
And light it.
It's, I wish I knew how to pause these things. Whoa. Whoa. Okay, I'll get back to that in a second. Let me explain about it. This is called a bacon lamp. So I thought I had the longer version of the video in there where we show the preparation. It's like a day-long cooking exercise to make one of these things. It's a device constructed entirely of bacon that cuts steel. Though actually, and I don't get a lot of complaints about this, but occasionally, it turns out it's not bacon, technically, it's prosciutto.
It's not smoked.
American bacon it's like it falls apart. It doesn't have any kind of structural integrity to it. But prosciutto is like, they're both ham, you know, and bacon is funnier, so I call it a bacon lance. And what it consists of slow-cooked prosciutto that's basically had all the moisture driven out of it, arranged in tubes, sort of concentric tubes with additional prosciutto around it, and then wrapped around the outside with fresh, uncooked prosciutto, which is airtight. And then the whole thing is connected
to a cylinder of
gas
oxygen gas.
manifold.
Let me turn the gas on and light it.
And then there's pure oxygen gas flowing through. Basically a grease fire is what it is. It's a grease fire fed by pure oxygen. And you can see when the sparks come out the other side, that's proof it's that true. of the steel. So, again, I wish I had a way of pausing it. You see the rubber, there's like a rubber hose fitting there that's holding the bacon in place. And it's really important that there not be any leaks anywhere through there.
I built another version using 7 beef sticks and a cucumber. Let's see how that one works.
Where are the beef sticks? It must be
Yeah, the cucumber is great because it's very airtight. It has like a rubbery skin. It would work. It works, but not quite as well as it might have. Anyway, the reason it's really important to have a very tight seal is because if any kind of gas gets out where it's not supposed to towards the end, then that part catches fire, and then you have the rubber burning, and that's really bad. So when you're preparing the meat stick for action, it's important to have a really tight fit with the rubber.
That'd be the jump on top, right?
Okay, so this is one where I'm hoping we're going to be able to actually do this demonstration here.
Yes.
So I'm not going to talk about too much here. Let's see. We'll skip this.
So what we've got magnesium shavings.
Yeah, we're going to
inside the dry eye.
right. We're going to actually do that, so we won't talk about it. So anyway, this column basically has been going for like 7-8 years now. After the first month that I'd written the column, I thought, you know, if I had about 5 years worth of columns, I could put them together into a book. So I thought I better keep at this for a while longer. And sure enough, 5 years later, like clockwork, I had enough columns, and we put it together into a book, Mad Science, which is down there, and which has also recently come out in paperback, which I think is why I'm here. I think that's why my publisher sent me around, but they don't actually have any paperbacks here, so you have to get it in hardcover. Anyway, so this is basically collected columns. It has all this stuff in it. And the subtitle there, Experiments You Don't Know But Probably Shouldn't, this is meant to be taken very seriously. My favorite review was a chemist who said, you know, he was fully prepared to poo-poo that statement because all of these books that talk about, you know, dangerous science you can do with your kids, you look inside and it's basically baking soda, vinegar, you know, volcanoes, and that's about it. I just got one that said, boom, things that explode that you can do with your kids. It's like, the potato can isn't even fired by hairspray. You know, it's a compressed air potato can. This book is not like that. This book is really, really dangerous. And it has, I think, an excellent 3-page safety section, which basically says you're nuts. You know, you're completely nuts to do any of this. But it goes into more detail about why you're nuts to do it, and why actually it's nuts for you to do it, but not me, which I think is somewhat interesting because there's actually lots of things that would be nuts for me to do, which would probably be fine for you to do. Like, for example, wingsuit cliff diving. Which is where people jump off cliffs wearing nothing but a bat suit. It has a 98% fatality rate, I understand. But some people are really good at it. And the videos they produce are mind-blowing. And those people should do that. I should not do that. Nobody should do that as a first experiment in skydiving. Right? If you're going to learn skydiving, what you do is you go on a plane really far away from any cliffs. And you do that a bunch of times until you're good at it. And then you start kind of getting closer to the cliffs. And eventually you might actually jump off a cliff wearing nothing but a bat suit. Some of these experiments are in that category. Like, if you've kind of edged your way up to it, and maybe you've got somebody else there who's done it before and can show you how to do it, then it's a reasonable thing to do. If you just read in a book about how to do wingsuit cliff diving and then go out and do it, you're going to die. Period. And it's kind of the same thing here. So this is my favorite example of an experiment of that nature, making salt. If you're tired of stale store-bought salt, and you want fresh salt, sodium chloride. Sodium, so you have a bowl of molten sodium, and chlorine. So we have a cylinder of chlorine gas. You have to melt the sodium because otherwise the reaction doesn't start. But if you melt the sodium first with a little blowtorch, and then you turn on the chlorine, they will react, and the white smoke that comes off is, of course, sodium chloride, salt. If you do it like I did, you don't realize that the net you have up there is made of a thermoplastic that melts. And then, of course, the popcorn falls into the molten sodium, and the popcorn has moisture in it. And if you know what sodium does with it, it's bad. And it took an effort to convince the art director not to put this on the cover, because this is such a beautiful picture, and I had to keep telling him, no, that's the flaming disaster. So they just used it small in the magazine, but in the book it gets its own 2-page spread because it is a really beautiful picture. This is a little bigger. It actually looks better in the stills and it moves so fast. You may or may not have noticed I'm wearing open-toed sandals. Which in retrospect, I don't know, but protected. See, it's not actually completely stupid. You notice from like table height up, I'm completely covered. The other thing I knew about this experiment is that there was very little sodium there. And we had 2 giant 4-foot fans behind the photographer, creating a constant airflow out of the studio and out. The only thing in this experiment that would actually seriously kill you is the chlorine. Everything else is like fire, whatever stuff blowing up. That happens all the time. That's not a big deal. The shop is set up for that. The shop is not set up for an uncontrolled chlorine leak. So as long as I got that valve closed, we were going to be fine. Which is why I closed the valve right away. So one question that comes up occasionally is like, why? Why? And I think there's actually a good answer to that, which is that, so Popular Science is not Scientific American, right? Scientific American is preaching to the choir. People like you, who are interested in science, who think it's interesting, who maybe actually got some science in school from a teacher who was not also your gym teacher. That's, however, not the people who read Popular Science. Popular Science is read by a very broad spectrum of people. And I think that being able to inject even a little bit of science into that environment, and Popular Science is not a science magazine, right? It's a gadgets and electronics and fast cars kind of magazine. Right. Nothing wrong with that, except the title. But if you can inject a certain amount of science, and actually I shouldn't say that because it's actually a really good magazine, and I'm amazed at the thoroughness of their fact checkers. I don't get away with anything, and I therefore trust what's in that magazine more than almost any other media outlet, where whenever you actually know what they're talking about, it's all wrong. I think Scientific American, or Popular Science, actually gets the science right an amazing amount of the time. Anyway, I think it's worthwhile to do it, to make experiments, to figure out ways of being competitive in this sort of really flashy, glossy world that these magazines live in, and giving them just a little bit of sort of breadcrumbs that people can Google, or little factoids that seem interesting that maybe some of them will follow up on. And so that's what I do. It may not be a lot of science, but it's a little bit, and it's what I can get away with. And I think sometimes people learn something. And there's actually a very long history of doing that kind of thing. So, the very first people who called themselves scientists, people like Joseph Banks and Humphrey Davy and Michael Faraday, these people invented the concept of being a scientist. It didn't exist before. There were alchemists and there were natural philosophers who learned, but the word scientist and the concept of being a paid professional scientist for a living was invented in Britain in the 1700s by people who were essentially showmen. What they did was they held public performances of science, which this is a picture of. One of the people here, and I guess you can't see my pointer, but one of the people in here is the prince and his kids, the Prince of Wales or whatever. He brought his kids to see this lecture about this new idea of let's study the world and understand it. And that tradition of presenting dramatic, exciting, perhaps somewhat pointless demonstrations of science has continued without interruption at the Royal Institution and has spread all over the place. This is a video of a show at the University of Illinois a couple years ago that I filmed. Audience completely packed with kids, all of them coming away with the idea that science is interesting somehow. Like maybe I could do that. Maybe that would be a fun thing to do. And if you get that idea across, that's huge progress. Let's see. There's more videos. This was one of Humphrey Davy's favorite demonstrations and inventions that saved a lot of miners' lives. The fact that a flame inside of mosquito netting will not travel through the mosquito netting even if the atmosphere outside is explosive, which is kind of cool. Anyway, I think it's worth doing because I think it's not at all clear that the current enterprise of civilization as we know it is going to continue. It's entirely possible that it'll just kind of turn out to have been a phase that we went through, and the forces of ignorance will take over again, as they had been ascendant for millennia before people thought it might be a better idea to actually understand how things work and think about them reasonably and make decisions based on reason and ration and scientific understanding, as opposed to all the other reasons and methods that people have of making decisions that typically don't work as well, but try to tell them that. I think it's important to kind of keep alive and spread as much as possible the concept that science is interesting, that it's worth doing, that it gives you answers that work. We're in a difficult time right now. So, we should all do our part. I think it is interesting to see that the whole, geek culture and the ascendancy of the nerd has really rubbed off into science. And it used to be, my daughter, who's 14, is proud of the fact that she's a nerd. And she goes to that kind of school, but nevertheless, I think this is an amazing achievement that the youth counterculture of being smart and nerdy has kind of come around, and maybe we're seeing the beginning of a new golden age. Yes, and I'm sure we are the presence of the vanguard here. The situation is not lost, and we're now going to skip over the slides that I would use if this were a talk to an audience of people interested in some of the business aspects of what we're doing. By Bjork, which we're very pleased with. Anyway, sorry, we're running into the part of the talk where
where I actually ran out of time to fix it up for this audience. So we're going to have some random things here. Oh, this is titanium thermite. Ordinary thermite is iron oxide, rust basically, mixed with aluminum. This is titanium dioxide mixed with aluminum. So instead of getting iron out, you get titanium out, for those who are familiar with the thermite reaction. The thermite family of reactions are definitely among the most attractive because they're not explosives, they're incendiaries, and they produce tremendous amounts of heat and sparks and light, and if you put them in pots that are thin enough, you can get the pots to crack so that the liquid metal then flows out all over the place. That's entirely intentional. Seriously. Right, okay, so what we're going to do is, we're almost at the end of the talk here, and after that we're going to take questions, and while I'm taking questions, I'm going to be preparing the final experiment of the evening, which is the magnesium burning in dry ice experiment, which is really cool. But it takes a while to do, so I'm going to answer questions kind of while we're doing that. But to conclude the talk, I'm going to play you what I think is probably the most peculiar and to future historians inexplicable cultural object that I'm responsible for creating, which is the Japanese translation of Tom Lehrer's Elements song. So for those of you that were here an hour ago and heard it, I promise I won't play the whole thing again. But for the new people, I think we have to play at least some of it. The reason we did a Japanese translation is because the iPad app is sold really well in Japan. It's actually the same tune. Turn down just a little bit. Sorry to disappoint those people actually wanting to hear it again. It's the Major General song from Gilbert and Sullivan, as is the Tom Lehrer original. This one, however, has been transcribed into Japanese, which is to say, an insufferably cute Japanese pop song. That's my second cousin once removed. Her name is Angelina, and she has a twin sister over here, Jennifer. They're 13. Because unbeknownst to me, for many years, I actually have a cousin who lives in Japan and makes his living as a lounge singer. He plays like piano in fancy hotel bars, and he has these two daughters who are my second cousins once removed, who sing really well. And so he was able to take the Tom Lehrer song and turn it into what for all the world is just the most. I told him, like, make me think of cats with big eyes, you know? Too cute, and then go a little farther. I think he did a great job. This song is about a minute longer than Tom Lehrer's version. 3 reasons for that. One is they couldn't sing nearly as fast as he could. 2, there's way more syllables in Japanese. And 3, there's way more elements than there were in 1959. They have like 10 more elements that they have to sing at the end. Like these. And we're completely current. We go all the way up to Capricium, which was only named last year. Okay, well, thank you very much. And now, ready for questions, and we'll try to do the demonstration at the same time.
Okay, let's give him a round of applause. Sorry. So we have a couple of mics. There's going to be one down on the bottom floor here, one up in the balcony. Please raise your hand if you have a question, and we're going to let him get started on preparing the other demo as well. So, Beth, okay, question actually up in the balcony.
Okay, I'll bite. The plutonium ring, what the heck is it for? Is it just pretty?
Oh, the plutonium ring, right. So that's a Lone Ranger, what was it called? It had a name. Anyway, it was a cereal premium in Kix cereal in 1947, I think. You get them on eBay. They go for like $100 because they're collectible. And what it is, it's called a spinthariscope. Inside the ring, if you take the little bomb fins off the back, this little plastic thing comes off, there's a tiny little glass lens. And you look through it, and at the other end of the ring, there's a tiny little phosphorescent screen, a zinc sulfide screen, and a tiny little speck of radioactive isotope that causes flashes on the phosphorus screen. These rings don't work anymore because they use polonium, which has a half-life of 138 days or something like that. So they've long since decayed. But they're outstanding artifacts of an era in which it was considered reasonable to put a radioactive object in the breakfast cereal. And they're much more attractive than anti-static brushes, which are where you can get actual polonium. You can actually buy bigger, spinthariscopes are fabulous things. You can buy bigger ones now from a couple different companies that actually work. And you go to a totally dark room, you have to let your eyes dark adapt for several minutes with absolutely no light. And you look through it and you see flashes like blah, 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 everywhere. And each one of those flashes is one atom decaying and causing one flash of light on the screen. And the discovery of this phenomenon, which was accidental, of course, as most discoveries are, was the first time that it was ever possible to directly observe with the unaided human eye the effects of one atom at a time. And it was therefore quite a an eye-opening experience for people who've been theorizing about atoms for quite some time to suddenly actually be able to see, and not only see but count, 1, 2, 3, 4, 5 atoms have just decayed. Yeah, you can get them. I highly recommend it. It's an amazing experience to be looking at atoms individually. Right. More questions?
How many science experiments have you done?
How many experiments have I done? Well, there's like 50 of them in the book, and I've been at it another, I don't know, probably like 100 or so, depending how you count. Although actually, technically, what I do are not experiments. There's a friend of mine who just got elected as president of the ACS, so I respect his opinions, who feels very strongly that I should not call these experiments because I know what's going to happen. What they are is demonstrations. An experiment is something where you try it and you don't know what's going to happen. If you knew what was going to happen, you wouldn't do it, because why would you do it? You know what's going to happen. So an experiment is designed to discover some new information. A demonstration, on the other hand, is meant to to show somebody else, demonstrate a phenomenon. And the difference is that in an experiment, if something unexpected happens, you get to write a paper about it, and it's great. In a demonstration, if something unexpected happens, you just screwed up. So what I do is demonstrations, and therefore we hope I don't screw up this one. This is not going to work. I can't hold this microphone and do this at the same time. So let's see how that works. Or a stand. We could try that. Make it.
Okay, is there another question? Right here in the middle.
How did you discover the importance of the airtight seal on the bacon lamps?
Experience. I've actually been getting better and better at the bacon lances. I've done them 3 or 4 times now. Actually, twice in the last couple of weeks, I have had to bake and ignite new bacon lances. One was there's a National Magazine Awards, which I didn't win last year. I was nominated, which is great, but I didn't win. And so this year they made me a joke in the awards ceremony, and they had me do a little video clip where they sent me one of these awards.
And I attacked it with a bacon lance and like vindictively destroyed it. And that didn't work. The bacon lance was not powerful enough, so I put it in a charcoal pit and poured liquid oxygen on it and just and here's the cruel thing. So first of all, I had this award which I didn't win, and I had to destroy it. And then they wanted me to send the molten remains back. It was like a puddle that I collected, and they gave that to somebody else who didn't win. So it's like I've been friend zoned really bad. I don't even get the molten remains of the award that I didn't win. Okay, more questions.
We got one in the balcony to your upper left.
So, what determines if you use a picture for an element or an actual, like a picture of someone's face versus an actual, like, hunk of it?
Oh, well, whether I could get a hunk of it. And it sort of coincidentally happens that, I mean, anything past plutonium, say, it's really hard to, I mean, americium is an exception, you can get that at Walmart, but anything else past plutonium, you either can't get it because it's incredibly illegal or incredibly expensive and illegal, or it just doesn't last long enough. You know, the half-life past 100 or so, they're measured in minutes, or when you get up to 112 or 15, whatever, they're measured in nanoseconds. So none of this stuff actually exists in the conventional sense of the word. I mean, the discovery of 113, for example, which is not yet named, is based on 2 atoms. The observation, supposedly, of 2 atoms that have ever been observed ever. So obviously I'm not going to get a picture of it. And I thought about getting pictures of like the apparatus that created it, whatever, but that's complicated. And I decided that people are actually much more interesting than their elements. I mean, people like Madame Curie or Lise Meitner, or any of these people, these are fascinating, interesting people. You don't get an element named after you just for nothing. So I thought they would be more interesting to put up there than some attempt at representing the element itself. Plus, it puts some human interest in there and attracts the non-scientists to my poster.
I wonder if there's a simple explanation for why the atomic radius shrinks as you move from what you think should be the smaller elements on the left side of a road to what should be the bigger elements on the right, but the atomic radius keeps shrinking.
Well, actually, it gets bigger and bigger as you go across, and then it gets small again when you go back to the beginning, I think. And it has to do with, or no, maybe it's the other way around. Yeah, it's the other way around, right? It's the other way around because as you're going to the right, you're adding more and more electrons in the same shell. They're different harmonics that have the same average distance from the nucleus. But meanwhile, you're adding more and more charge to the nucleus, so it's sucking the electrons closer and closer. And it's not, adding more electrons isn't causing it to get bigger because they're all just different orthogonal harmonics within the same shell. But when you go to the next row, you're now starting a new shell, a new energy level, much bigger around. So it kind of jumps up. And then you progressively make them smaller and smaller, with all the little exceptions that always pop up in there, where things don't quite fit in the shells they're supposed to. But it's basically because fundamentally everything is getting smaller because the charge in the core is getting bigger and bigger, pulling it in. But then you're stepping up because you're adding new shells around it.
Do we have one upstairs?
Not at the moment.
Hi. I feel like you should be a walking safe cone shirts ad. But aside from that, I wanted to ask if there was ever like a demonstration or an experiment that went horribly awry and you were just like, WTF, I did not think that would happen.
So here's my attitude about safety. I have never been hurt by a chemical, and I've never come close to being hurt by a chemical. Many things have gone wrong including spectacularly wrong, like the salts there, where the thing, just, I did not anticipate the salt, the heat melting the net and the thing dropping, moist popcorn into molten sodium. But no one was anywhere close to being hurt there, because I anticipated that stuff was going to go wrong. I didn't know what exactly, and I was prepared, to have a certain level of damage, to the shop. I was not willing to have the integrity of the chlorine cylinder in question, because that would have killed us. So, there was never any point in that experiment where there was any possibility of the chlorine cylinder going wrong. And, that's how I try to set things up. I'm actually a complete ninny, and I'm secretly terrified of all this stuff, which I think is important if you're going to do this on a regular basis. I mean, it's fine to take risks every once in a while just for the hell of it. Like you get a new car and you go 100 miles an hour for fun or whatever. But if you're going to be a race car driver and actually do that regularly, then you better be wearing a 5-point, strap-in harness with roll bars and practice a lot at slower speeds and really know what you're doing. And just be neurotic about not killing yourself if that's what you do. So, yeah, the answer is many things have gone terribly wrong, but I've never had something go sufficiently wrong that I felt significantly in danger, which is not to say that it won't ever happen. Anything could happen. But I think I'm probably quite a bit more likely to get run over by a bus or something like that than hurt by one of these demonstrations. We'll find out with this one.
So, for someone who is applying and hoping to become a chemistry teacher soon, I know I only have a very limited time to catch my students before they are, shall we say, lost and convinced that this truly is boring. What do you recommend in the first week for chemistry demonstrations for a high school chemistry class?
Hydrogen soap bubbles are hard to beat.
It's true.
Self-cooking waffles. Self-cooking waffles. I don't remember the element, but there's one where you can put into the waffle batter and it'll cook itself.
Really?
Yes.
I would like to know that.
I'll find your email and Google it.
Yeah, well, he claims that there's a recipe for self-cooking waffles. And I would very much want to know that recipe now. I haven't heard about that. I mean, there's a number of things that cook themselves, but I haven't heard of waffles. And I wonder if you can eat them, too. Because if you could have self-cooking waffles that you can't actually eat, that would be revolutionary.
I don't know about that one, but I do know about explosive pancakes you can eat.
Really?
Yeah, it was special on the History Channel.
Huh. The competition apparently is upon me.
If somebody wants
television or something,
Google that on their smartphone and give us the URL, we might be able to pull that.
That would be great. Let me just do a little more drilling here so we can actually make some progress on this. I need to make a hole.
Another question up in the balcony.
No.
So, it's not like self-rising.
What was your most challenging or difficult element to collect?
Hardest element. Well, I mean, there's some I haven't got yet. I mean, this, Technetium, I think, is the one that I don't have, but which I could have, both legally and by the laws of physics. And I've had a couple of close leads, but it is radioactive, and the isotope that is commonly available is very short-lived. There is a long-lived isotope that you could have like a lump of it, but it's almost impossible to get. I haven't gotten it yet. So Technetium would be there. I have little foils of it, but that's not really satisfactory. Plutonium is possibly the most frustrating in the sense that I could have had several samples of it, but I had to turn them down because it's
really, really not legal to have plutonium. And the way this comes about is if you look at my site, you'll see there's a plutonium battery that came from a pacemaker, and it's empty, which is why I have it. But it at one time contained 3 curies of plutonium, which is a lot of plutonium. I mean, not enough to make a bomb or anything, but it's just a lot of radioactivity. So these are thermoelectric batteries. They use the heat of the plutonium decay to generate electricity to power a pacemaker. And there are said to be, or at least a few years ago, a couple dozen people left in the United States who still have plutonium pacemakers implanted in them. Modern pacemakers use lithium-ion batteries and are rechargeable. These would last forever. And the law says that a private citizen can possess plutonium only if it's implanted in their body in a pacemaker. If you die, you have to give it back. And so undertakers who are asked to cremate bodies of people who have pacemakers in them know that you have to take the pacemaker out. Therefore, all undertakers have a desk drawer with pacemakers in them. And some of them notice that the pacemakers have little radiation symbols on them. And some of those people Google plutonium pacemaker battery or plutonium pacemaker, whatever. And those people find my website because that's what Google takes you to for my empty battery. And 3 times so far over the years, I've gotten emails from two undertakers in one hospital in Texas asking if I would like the pacemaker to add to my collection with a live plutonium battery in it. If I ever said yes to any of those people, it would be really bad because you just can't do that, and it's plutonium, and we're in a post-9/11 world, and I'm a ninny. So I send them all the law. The law says all plutonium must go home to Los Alamos, where they will love it and take care of it. And the regulations are really quite strict on this. So plutonium is like near misses, but my basic wimpiness gets the better of me, and I tell them no.
Keep on the question underneath the document.
Okay, we're going to do kind of a baby version of this because I actually thought we were going to be doing this in like a science lecture type thing because nobody told me it was a bar. So we're going to do a relatively smaller version of this in case it goes wrong. What I'm doing now is carving the ear channels because I want to get the smoke to come out the side of his ears. We're making a face here. If you see what I mean here. Normally I would carve this a little better. We're making a face, and we're going to stuff the back of it with magnesium shavings. And I want the steam to shoot out the sides like in the Dilbert cartoon. Okay, so we carve the ear holes.
Chris, there's a question.
Question?
Yeah.
How did you come up with the idea of the beef or the bacon stick? Bacon lance.
Bacon lance, okay.
How did you come up with that? And then how did you pick cucumber afterward?
Okay, so you have to understand, there's a thing called a thermal lance, or a thermic lance, depending on who you believe, which is it's a serious professional tool designed for really difficult demolition jobs. If you have steel, you want to cut up steel, you can use an oxyacetylene torch to do that, because once you light the steel, the oxygen will cut through it, it just burns, and it's relatively easy to disassemble steel structures. If you have, let's say, reinforced concrete, where you have a mixture of steel rebar encased in concrete, and let's say there's been an earthquake and the thing has collapsed, or you just want to take it down, this is much harder, because an acetylene torch, it delivers a high temperature, but not enough heat content to actually melt through the concrete. So there's a thing called a thermal lance, which is basically a pipe. They're usually like 6 feet long to start with. Iron pipe, just like water pipe, packed with iron rods. all the way through the pipe, and sometimes mixed in magnesium rods as well, and then a hose and oxygen gas. And you use a welding torch or a battery or something like that to ignite the end of this, and the flow of oxygen actually burns the iron, it consumes the iron, reacting with pure oxygen, which iron will do at a high enough temperature. And it jets out this white hot iron plasma that is so hot, not only high temperature, but high heat content, that you can melt through rock with it at a decent rate. And it can therefore be used for demolishing things that's impossible to do with an acetylene torch. This is a demonstration of the fact that oxygen is an incredibly powerful oxidizer. What happened to my glass of water? I have water. My throat's getting scratchy. So it's a demonstration of oxygen being a powerful oxidizer, which is an interesting scientific principle. However, it's not funny. And I needed to think of a funnier way of doing it. And I actually saw a YouTube video of a guy who made a spaghetti lance, which was basically a package of spaghetti wrapped up in tinfoil with oxygen gas. And he was able to scorch his patio furniture with that. And this was an advance, but I felt it was not funny enough. And so I was trying to think of what fuel source could you use, because it really doesn't matter what fuel. If it burns, it will burn better in pure oxygen. And the funniest fuel I could come up with was bacon, because the internet is all about bacon. And, I thought it would be funny. And then I thought that I would get complaints from, PETA and people who felt that it was inappropriate to treat bacon this way. I don't know. I'm not a vegetarian, I'm sorry, but I thought that I should develop some less offensive versions of the lance. I had a completely vegetarian version, which is breadsticks in a cucumber, and it worked fairly well, but you really need fat to get a lot of concentrated energy, and that's why.
Avocado.
Garlic bread. Well, I got the most greasy kind of buttery breadsticks I could find, because it's basically calories, right? You need fattening food if you want to get through a lot of steel. It's the exact same energy that we're talking about. So high-fat bacon is really an ideal material, and it's funny. So that's the origin of that. Okay, I think we're just about ready. I'm going to add a fuse here. So what this is demonstrating here is that is why you should not use fire extinguishers on metal fires. So we're gonna have burning magnesium, and it's going to be burning not in the air, which it will do also, but rather inside of a block of ice, of dry ice, CO2. Because it turns out that magnesium will actually react more strongly with dry ice than it does with oxygen from the air. And so, one of the things that fire extinguishers use is carbon dioxide, because it will smother most flames, but not magnesium flames. It makes them much worse. We need the other block here. So this is also an example of a classic chemistry demonstration that people do, and which I'm just kind of doing in a somewhat spruced up way. Usually it's done with the blocks horizontal and no face carved in it. When I do it, I usually carve the face better. And I stand them up like this. Now the big unknown here is whether it's going to shoot any little bits of flaming magnesium out the sides and set the stage on fire. Right. So what we're doing to mitigate this is, first of all, it's probably not going to shoot any flaming magnesium out. And there's very little magnesium there. So in the event of something that's not supposed to burn catching on fire, it won't be magnesium burning for more than a few seconds.
Move the mic stand.
Move the mic stand, good idea. Okay. Actually, it doesn't matter where the lights are set, because this thing will be much brighter than any of the lights if we do it right. And in fact, it's so bright that there are people who feel you shouldn't look directly at it. I think the thickness of dry ice is such that it's not actually a problem looking at it. But again, if you don't feel like you should be, don't. Right, so and this is a good example, right? This could set the stage on fire, but that's okay, because we have fire extinguishers there, and right, there. We have one fire extinguisher. Is it charged? What does the little dial say?
Yes.
What kind of fire extinguisher is it? What does the dial say? Not the tag, the dial.
It's an ABC.
No, but I mean the pressure gauge.
Yes.
Very good.
A glass of water works on a burning stage.
Right. Yeah, see, as long as the metal is burning, we're better off doing nothing, because that fire extinguisher may or may not improve it. But the metal won't burn for very long. And then, as long as no one panics, we'll just put the stage out. Also, this part is soaked in water. All right, so let's light it and just see if it works. The other bit about never relighting a firework doesn't apply to magnesium.
Wow.
Okay, very good. Well, so normally we would put a lot more magnesium in, and this thing would have kind of shot more, but it seemed prudent under present circumstances to limit. And you notice we did have some little flaming bits of magnesium shooting out here to the side, which landed harmlessly on the soaked
Good job.
canvas here. And by the way, the smoke, most of the smoke that you saw was dry ice fog, essentially. The stuff that's lingering is milk of magnesia, basically, magnesium oxide, which combined with water becomes, so it's harmless. It will lubricate your lungs or something. Okay, well, that's it. Again, I'm happy with it not having been into that for the first time.
So, more questions?
I'm happy to answer questions as long as people
We have
stay.
one underneath the balcony and the way back.
So, besides writing books and giving these talks, do you do anything else?
Well, yes. So this is actually I don't know how many of you are familiar with Mathematica and Wolfram Research. So Mathematica is kind of high-end technical computing software, and Stephen Wolfram and I co-founded that company, Wolfram Research, in 1988. So technically, I'm in the software business. That's what I have always traditionally referred to as my day job. And it was actually what I did most of the time up until last year, when the Elements book, in particular the Elements iPad app, started kind of taking up a lot of time. And back just about a year ago, we founded a new company, myself and a partner, Max Whitby in England, and Stephen Wolfram and some others, called Touch Press, which is an ebook publishing company that is the publisher of the Elements iPad app and the Solar System iPad app, which you saw a little bit of. and just came out a couple weeks ago, Gems and Jewels, which is currently iPad App of the Week. If you go to the App Store, you'll see it right there, huge banner. That's our third product that we've released. And we have a fourth one, the Wasteland, the T.S. Eliot poem, which we have a beautiful iPad app for that will be out in a couple of weeks. So basically, these days I'm an ebook publisher, which is, you know, I guess it's a job. I think it's a job. It's certainly, you know, it's more than a hobby. And someday I might go back to mathematical software, but for right now I'm being a publisher.
Yes, earlier you mentioned a couple of different thermite reactions, one with iron and one with titanium. Have you used any other metals for thermite style reactions?
I haven't. I've seen people who have copper thermite, copper oxide plus aluminum seems to have a tendency to explode a little bit more than I like. I've seen a couple of different ones. I mean, it can be done. My friend Max actually, at one point was seriously talking about doing it with thorium, which I thought was a really, really bad idea, because if it went wrong, you'd then have your entire backyard scattered with radioactive thorium. But he was that desperate to get a hold of thorium metal. I found him a better source. Anyway, it's a whole class of reactions. You can do it with a wide range of metal oxides, plus typically aluminum or magnesium. But iron it's really, you know, I think the nicest of the thermite reactions, because it's very predictable, it's very reliable. You can tune the heat easily, and you can do it using beach sand. I collect it in Santa Cruz whenever I'm there. Titanium thermite actually doesn't burn nearly as hot as iron thermite, so you have to add plaster of Paris. Interestingly enough, gypsum reacts with aluminum more strongly than the titanium, and you can use it as a heater to basically increase the temperature of the reaction and get the titanium thermite to work better.
Have you accidentally discovered anything while doing your experiments and demonstrations?
Have I accidentally discovered anything? I don't think I haven't discovered anything useful. I think I've discovered, I think it's fair to say, a number of more interesting ways of demonstrating certain things than other people have thought of. I don't think I've actually made any contribution to the world in the sense of, you know, useful discovery. No, not that I can think of. But, you know, whatever. It's a living.
Okay. So you talk a lot about emphasizing safety, you never quote yourself, but of your experiments, which has had the most potential for going wrong, and or which of your experiments, or demonstrations rather, have required the longest setup and most intricate for you to create?
So the question is, which of my experiments has the most potential for danger, and which one has required the most elaborate setup? There's a couple different factors that go into whether an experiment has a potential for danger. One of the most important ones is accessibility of the ingredients. So, for example, the making salt. You know, if you take a cylinder of chlorine gas and open the valve in a closed room, you could very well kill a couple dozen people quite quickly, and cause, you know, permanent respiratory harm to the rest of them. So if you got a disgruntled kid in a school with a cylinder of chlorine, you know, that could be really, really bad. But on the other hand, it's hard to get a hold of a cylinder of chlorine. You know, you can't just go out and buy it in the store. Unlike, for example, guns and ammunition. So, you know, I mean, this is one of the things about all these sorts of experiments is that we live in America here, and yes, it's possible to make gunpowder using ingredients from a garden center, which is an article that for some reason never let me write. And it's possible to construct extremely elaborate, destructive, and dangerous devices. But you can also just go out and buy a handgun legally without a background check in half the states, or court jugs of gunpowder at Kmart. No questions asked if you live in Texas. So, you know, in terms of access to dangerous materials, science experiments are way down on the list of accessible dangerous materials. And in many cases, the potential for danger is limited just by the fact that it's hard to get this stuff. I think the other thing which I emphasize very strongly in the safety section that obviously everyone should read, is that people kind of have to be responsible for knowing what it is that they ought to be doing and what not. And everywhere else in the world, people seem to take this for granted, that, you know, kids ought to know whether they're old enough to cross that 4-lane highway on their bicycle or not. You know, kids ought to know if they should be out after dark in certain neighborhoods or whatever. But with science experiments, somehow it's gotten into people's heads that it's the responsibility of anybody who's writing about it to not write about something that could potentially harm somebody. But, you know, that doesn't make any more sense than not writing about any other sorts of topics that people ought to know about. Let's see, I'm kind of rambling there. So which experiment required the most setup? I mean, there have been several. Probably the most elaborate one was testing this bomb-proof wallpaper that I did for, which is actually not a chemistry experiment, but Popular Science asked me to do a photo shoot testing the efficacy of this secret military bomb-proof wallpaper. So we had to build a whole elaborate apparatus to hold miniature brick walls and smash them with wrecking balls with and without wallpaper. And it turns out the stuff is amazing. You can just smash it and the brick wall bounces back off the wallpaper. But that took days and days to build. What else has taken a lot of work? I don't know, there's various ones. I try not to spend more than a few days on each one because it is just a hobby. I'd say that's the most elaborate, is the wallpaper.
Okay, any other questions? Well, we're just about out of time anyway, so I think with that we will say thank you to Theodore Gray.